All buildings have a natural period, or resonance, which is a number of seconds it takes for the building to naturally vibrate back and forth. The ground also has a specific resonant frequency. Hard bedrock has higher frequencies than softer sediments. If the period of ground motion matches the natural resonance of a building, it will undergo the largest oscillations possible and suffer the greatest damage. Small buildings of 1 or 2 stories resonate naturally at much less than 1 second periods. A 1 second period will affect buildings of about 10 stories. For example, a 30-story building resonates at a period of 3 seconds, and a 50-story building resonates at a period of 5 seconds. During the 1985 Mexico City earthquake, the ground beneath the city resonated with a 2-second period for over a minute. Thus, medium-height buildings with similar natural periods suffered the most damage, while short, old, weak stone buildings and skyscrapers were relatively undamaged. That proved to be what is called a resonance disaster, which is how engineers describe the destruction of a building by seismic vibrations at a system's resonant frequency. It is because of prolonged energy input that the system swings more and more strongly until a structural load limit is exceeded. A key point here is that small buildings on hard rock and large buildings on soft sediments may suffer more damage and ground motion effects from an earthquake than small buildings on soft sediments and large buildings on hard rock. Resonance is one factor that contributes to earthquake damage. Of equal or greater importance are building design and the quality of construction materials. By determining the resonant frequency of the ground beneath the building site, the building design can be modified so that a resonance disaster does not occur. The following demonstration shows how to model resonance in the classroom.
The idea of the BOSS model is that different height buildings will respond to different frequencies of horizontal ground motion. A tall building will respond to very slow or low frequency oscillations of the ground. So if I move the base slowly back and forth, I can get the tall building to oscillate, where the intermediate and short buildings are not moving. If I move it more briskly, I can dial in the rate of horizontal oscillation so that I move the center building, the intermediate height building, and the short and the tall ones are barely moving. To get the short building to oscillate, you need to move the base very briskly back and forth and dial in to the natural frequency of the short building, and we can see that the intermediate and tall buildings are barely moving.
House built on a weak foundation will not stand, oh no. Stories told through all creation will not stand, oh no.